So good evening. So today we'll be discussing our next topic, which is linear regression. How to find the values of M and C? Like we had this question. Now let us come to the learning part. Okay. So we won't be doing a classification straight away. We'll be starting with a regression task, which means I am predicting a continuous value. Let us say like weather tomorrow. If I ask you what will be the weather tomorrow, then you make your model, which will be what will be the input to the model. Maybe today's weather, today's humidity, yesterday's weather, yesterday's humidity, and like that, you can take all the past data. That can be your input. You have to choose what size of data you need. If you take very huge data, then again your model will be very large and difficult to deploy. Okay, so you want to predict tomorrow's weather. Like this is one example of a regression task. Another example which I'm showing here is, let us say I give you a relationship. Basically, I give you some x, feed it to the model f, and it gives me some output y. I repeat this operation, let's say 5 times. Means I give an x1, it gives me a y1. I feed in x2, and the model gives me a y2. In this way, I do it 5 times. I feed in an x5, the model gives me a y5. And now I want to use this much data only to find f of x or y for any x. Is it possible? Just given this finite set of samples, a finite 5 samples, how can I estimate my y for any x? This is a regression task, right? If you compare it with the temperature forecasting task, like I give you temperature of past 5 days, I want to ask what is next day's, tomorrow's temperature. Okay. No, I'm sorry, it is not equivalent. The equivalent problem will be, I give you temperature of 5 days and I ask you, okay, tell me temperature at any time within these days, or maybe at any day. No, still it is not a good. No, it's not a good example. Yeah, exactly. So what you can do is you can say this is my time and this is my temperature. Let's say from t equal to 0 to t equal to 5. Let's say the units are days. I give you just 5 samples, here, 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 and I ask you, tell me temperature at any of these, at any time instance. That could be an example of regression here. Okay, how shall we do it? Okay, so let us come back to the sinusoidal example. All of you have read Taylor's theorem, right? What does Taylor theorem say? What does Taylor theorem says? What does it say? It says that you can approximate any function with Taylor series approximation. Okay, so just take some inspiration from that and come to this model, and that inspiration will kind of to motivate that why I chose a polynomial model. This is a polynomial model, which means that your input is polynomial. It is x to the power 0, x to the power 1, so on up to x to the power d. And these are my unknown parameters. So let's say if you have your f, you have your y, you have your x. So my y is this form. Let's say x transpose w. Oh, sorry, this is not the right way to write it. I can write it as and W is W0, W1, so on up to W. Right? I can write it like this. Okay. So this is, and I can write this also in matrix notation. Okay, but before that I will do something else. So let us say I have got x1 to x5. Right? Can I say my y1 to y5 is something like this? 1 x. Let me just confirm the. Okay, fine. Oh, sorry, it is WD, not W to the power D. So I can write it like this, right? So let me represent this like, I call this as vector y. This is my vector notation. I call this a matrix phi, and I call this a vector w. So I can write it like this, all my 5 samples, right? Is this clear? Okay. I won't go to my slides yet. Okay, so here we have represented y in this form. Okay, now let us assume that capital D is 4. Let us assume capital D is 4. How many unknowns I have? How many unknowns are there? Huh? How many unknowns? D plus 1 unknowns. How many equations are there? Which are like, these are W0 to WD. Right? How many equations are there? 5 equations are there. All of you have read Cramer's law, Cramer's rule. Huh? What does it say? It says that if you have 5 equations and 5 unknowns, okay, linearly independent equations, 5 equations and 5 unknowns, you can find a unique solution. If you have less number of equations, more number of unknown parameters, then you find infinite number of solutions. And if you have more number of equations, less number of parameters, then you have no solution. They are in linear independent equations, right? So that's why you won't have any any solution. Okay. So let us look at this example. If you have, okay, if D plus 1 is equal to 5, then what will be the solution? Y is equal to, means we know y equal to, okay, y is equal to phi w. What will be my goal is to find the value of w, right? What will be my w then? W is equal to phi inverse y. Unique solution. Okay, so this case is fine, but what about the case when you have more data, less number of parameters? Means more equations, less number of parameters. You cannot find a unique solution. You will not find any solution. What can you do at best? you can minimize the error. You can make it as best as possible. Let me try to fit all the equations with least error. What I can do is, okay, so here there is nothing special about 5, it could be n also, right? This could be any capital N. If d plus 1 is less than capital N, then no unique solution. But what I can minimize is, let us say my actual value is t and my model says y. Okay, so this is my model, right? I also have my actual values. That is a target value. Target value means okay. Let us see here. So if I choose any x, like let's say this x, like this is my x, let's say x1. So this will be my target value, t1. And what is y? Y is the estimate. y1 is the estimate. It may or it may not be same as t, right? So actually, when I am taking my training data, it should be t1, not y1, because okay, I am in training. I know the actual value. I know the actual target value, right? And y is my model, so y is my estimated value, right? This could be different from my target value. Okay. So now coming back here, if my d plus 1 is less than capital N, is less than the number of equations, then I cannot have a unique solution, but what I can try to minimize is the error, like t minus phi. Can I minimize this? Right? So can I minimize this? Right? So yes, depending on the value of capital D, if my capital D is very small, I can minimize it to a large value. Means my error will still be very large. Even the best error will be very large. If I increase my model size, if I increase my capital D, then I can estimate better and better until I reach capital N, when I will be able to estimate perfectly, right? And what happens beyond that is a different story. I will tell a little later. Okay, so this is what we get. So I have got a y which is phi w. We defined this. Now my error, I can define it like this: target minus y. My y is phi w, and this means this is equal to basically t vector minus y vector whole square, right? I can represent it like in the vector format, t minus phi w transpose t minus phi w. Now, how do you find out a maximum or minimum of any function? You differentiate it and find the slope. When the slope is 0, you say it is the extremum point, whether it might be a maximum or a minimum. And then how do you find out whether it's a maximum or minimum? You take a double derivative, and if the double derivative is positive, you say it is a minimum. If double derivative is negative, you say it is a maximum, right? So you have either a minimum or a maximum. So the slope is 0 and the double derivative is positive, it is a minimum. And double derivative is negative, it is a maximum. Okay. In this case, I want to find the minimum of this. I want to minimize my error, right? So how will I do it? I will differentiate it with respect to the learnable parameters or the unknown weights or the W. So now this is a matrix or a vector calculus or a matrix differentiation. How many of you know matrix differentiation or vector differentiation? Okay, not many. No problem. So we have Wikipedia, which has got a good cheat sheet. Maybe I can open it. I can see if I have it. Yes, I opened it just before the class, so that we can quickly see. So the title is Matrix Calculus. So you can derive these formulas very easy. So how can you derive them or how can you verify them? You just expand them and see they match, right? So how do you differentiate a vector by a vector? So these are the identities. I will explain them as we go through them. Okay, so here. Now, I want to differentiate this thing. This is something, some vector transpose into vector, derivative with respect to a vector. How do I do it? So this is of the form, there is a vector called U transpose V, right? U transpose V, derivative with respect to some W. Oops. So if you derive it or if you look it up there, what you will find is, okay, it's a partial derivative. So this will be dou U by dou X or W times V plus dou V by dou W times U. Right? In our case, U and V are same. So what you get is twice of this whole thing, right? So you get twice of, so this is dou U upon dou W times V, and other thing is same. So it is it clear? This formula is something, okay, take it from me now. You can verify it. And this is what you can. You can also derive the same form using element-wise representation, right? Instead of writing matrix sum, you can write summation over some index I, and then sum them up all. It will give you the same answer. I have done it. If you want, I can show you the derivation in that way also. But this is a nice way because it involves some matrix calculus. It will be useful for other things as well. Okay, so this is what we get. Now, how do I do this? Dou W, T is independent of W, so this can go away. This will be 0. Now, phi times W. Okay, now here I have to differentiate. I have to differentiate this. Phi is a matrix and W is a vector. So let's say I have a matrix phi and a vector, let us say U. What will be this? So this will be given by dou U this will be given by dou U by dou W times phi. Phi transpose. Okay. You can also see the dimensions. So let us say my phi is m cross n, then U has to be n, and my W is n cross 1. So when I differentiate this n with this n, this becomes n cross m. So in this way, my dimensions are consistent. You can do this. In case you don't understand, we can go over it once again, but this is simple. Okay, so now you have got, so this is what you have got. So you want to differentiate this with respect to this. So this is u is same as w's derivative is 1, and my phi becomes phi transpose, that is it. And this is you already have. Now you open the brackets and you get this. So derivative is equal to 0. You minimize, you get w is equal to this form. Correct? So this is called least square solution. So this solution of this value of w is called the least squares solution. Okay, Okay, I implemented this on Python, and for the same problem, sinusoid estimation, and I have some plots for you. So in this case, in both these cases, my n is 3. I have 3 equations and 5. D is 5, so means 6 unknown parameters. And this is my data. I have sampled 3 points from the sinusoid. This is what I got, 1, 2, 3 points, and the yellow one is the true value. And when I trained, while training, this is my estimate. The green ones are the estimates. It does very well, but if I try to see on unseen points, it does very bad on the test set. On the training set, my error is very small. See, it is able to minimize. I use this equation, this formula. It is able to minimize, but on the test set, it is very bad. Similarly, for n equal to 5, d equal to 5, I know that this is a same number of equations, same number of parameters. So I get very good fit. If I increase my number of training points to 30, very large value, keeping my model size as same, I get a very good fit again. What does this show? So in all these examples, I have kept my d to be 5, my model size is same, and I am increasing my number of points, training points. And what am I seeing? Look at this, the test set. The test performance is so bad. The test performance improves, the test performance is better. So my test performance is improving as I am increasing my number of training points, right, for the same model. And this is the general trend. This is the error on the y-axis, the mean squared error plus 1 log. So this is the error, and this is the number of training points. I took 3 points here, the error was very large. 5 points, error was almost 0. With 10 points, almost 0. 30 points, almost 0. So as I am increasing my data size, my model is able to learn better and better. Okay, let us now do the other way. Now I have fixed my training data. I have 5 samples only, but I am increasing my model size. Now, when my model is very small, d equal to 0 means only single w0, right? I have only single trainable parameter w0, which is a constant, right? So if I find whatever value I will find, it will just model the whole thing with that. So this is my training data. It cannot even fit the training data because model is very weak. On the test data, again you see same value and it does not fit. Let us increase my model size. Now I made model size 1. Training points, same 5 training points. Now on the training data, my model is able to do little better because now it has got an M and a C. And earlier there was only an intercept. Slope was always 0. Now we have a slope also, so it can also tilt. So I have got a tilted lines, a slanting line, and it is able to fit the data. So on the training set, it is trying to minimize the error in this way. On the test set, it is performing bad because the model is weak. I increased my model size to 4. D is 4, so means 5 unknown parameters. Now it is able to do much better, right, on the test data. Okay, but something now. If I make my model very strong, let's say 10 points, this is interesting, please pay attention here. If my model is very large, what happens? Theoretically or intuitively, what I imagine is that the model should improve, right? my performance should improve because my model is very powerful now, and even with less data, it should do better than my weaker models. But what I see is, no, it doesn't do that. It is performing worst. With a model size of 10, the error is very high. Model size of 12, error is even worse. Whereas with the model size of 1 or 3, it was still less error. So what is going wrong here? By increasing my model size, my training is becoming poorer. My model is becoming poorer and poorer. So if you look at the test data, this is how it looks like. So it is able to fit the training points very nicely, but in the test points it is showing garbage. I'll show you an example. So I would recommend the Bishop's chapter that very nicely explains this point, the first chapter of Bishop. Let us say I have got, okay, let us work with this one only. So let us go back to the previous slide. So in this one is fine. Okay. In this one, this has got 5 things. Okay. It will try to fit something. Okay. I'm sorry, I should come back to this example. So in this one, what it will do is it will do a very it will try to fit every point and not considering what is happening at other points. That is what you are getting, like something like this. So this is going all the way up, right? This is called overfitting. So you are fitting your training points very well, but your curve is so spiky. It is taking so sharp curves, and it is on other points it is just not able to generalize well. So it is not able to generalize to other points. Right? And if you look at the weights of this thing, you will find that some values are very large, some WI are very large. So that's why one way to avoid this problem is by limiting the weight size, so that the weights are small, then the behavior will be less erratic and it will be able to fit better. So what we do is we put this down. See, it is the same function here, the same error function, but here I have added an extra term which is W transpose W. So I'm not only minimizing the error, or means the least square error, the squared error, but I'm also minimizing my values of W. It is minimizing W square, each W square means for each W. So, and lambda is some controllable parameter. This is a hyperparameter. This is a hyperparameter which is in my control, which I can control. Okay. So you do the same derivation. You differentiate it, you get this term. You differentiate this, you get this term. And then you know you have to put your dou E upon dou W is equal to 0. And this also can be solved, and this is what you get. So the same solution, this part is the same as previous one, just that you have got an extra term here. This is an extra term because there was this extra term, right? So technically this is called ridge regression. Okay. Why? Because we have this squared term. Okay. I will stop here.